So what I'm going to do today is, just like that very nice introduction gave, I'm going to be a chemistry bore. So this was supposed to be about, the conference is supposed to be about the new mechanism. I'm going to come along really and just talk about mechanisms in chemistry. It's a very practice focused, the practice of a particular science, and the very much more specific things you can say about them. I've got some very specific things to say about reaction mechanisms in general across organic, physical, and inorganic chemistry. Most of my examples though will be from organic, just because they look better. So basically what you'll see if you look into a chemistry textbook under mechanisms, the kinds of things I'm talking about, the diagrams and the explanations, they're the things that you'll see. And Nobel Prizes have been given out for these kinds of explanations right back to the founding of the award to the Nobel Prizes. So there's a long tradition of mechanistic explanation in chemistry, but it means something very specific. And because of all the things I think about, you know, the world according to chemistry, things have to be that way. So as I say, I'm going to concentrate closely on the practice of chemistry, and we can ask afterwards how all this relates to more general conceptions of what a mechanism is or could be. As far as I can tell, it's got little to do with clocks, so with that kind of 17th century kind of mechanism, and that's partly because a lot of the organization that you get in a chemical chemical reaction mechanism is ephemeral. So it comes into being and it passes out of existence at the end. So it's not something, you know, sitting there underlying the production of the phenomena. It's something, it's structure, it's organization that comes into being and then goes out of existence. So it's ephemeral. The second thing, I mean, this is like to refer to some of the things that came up in Brigitte's talk. Classical mereology has got little to do with it. It's got a little explicit role. It just doesn't come in. We'll mention it once, and that's only to say, well, actually, that's no use here at all. In terms of the new mechanism and the concentration on that, there are plenty of entities and activities and the exercise of powers we're going to see, but in a way that's, I don't know how informative one finds that, given that we've got something much more specific to say, which is what I'm going to say. That's a bit like, you know, we're all speaking prose, as it were. Right, so what are my claims? And now I'm hitting return and it's not moving on.
Maybe, oh, okay.
That's it. So here's 4 claims about mechanism. I found out which lever to pull. So here are 4 claims about reaction mechanisms in chemistry. Firstly, a reaction mechanism is a way. That's how I think of it. Maxim. I mean, maybe this modal talk is too attractive. I mean, I also think of substances, chemical substances, as ways that portions of matter can be. So they have a modal conception of what a chemical substance is. They're kind of structured, organized matter. A reaction mechanism is a proposed description of how a chemical reaction might possibly happen. And of course, it's going to start with the reagents and it's going to end with the products. Reagents and products here thought of as chemical substances. Now, here's a second claim. Here's a claim. I'm not going to defend that here. I've defended that in another paper that I've been saving up for a while to put into a book. And this is basically something that anyone who's interested in classification will recognize as microstructural essentialism. But I make the claim only about chemistry, and more broadly, I'm a pluralist about classification, because I think that classification it seems obvious to me a priori that classification must work in different ways in different disciplines. So in chemistry, I think there is a close relationship, chemical substances, between chemical substances and its structure at the molecular scale. So chemical substances are the particular chemical substances they are, and not another one. So water is water in virtue of its structure at the molecular scale. That's what makes it what it is. When you think about that, then a reaction mechanism then must be a series of a process that gets you from reagent structure to product structure. It is just obvious. So, but there could be different ways of getting from one thing to the next, and I'll talk about that in a minute. So you can have different pathways from reagents to products, and they are individuated by the different ways that they're composed of a few basic kinds of step. And here's my second informative claim: all of those basic kinds of step, and so hence reaction mechanisms are general, can involve transfers of such conserved quantities as mass, charge, and energy. You just see those in the diagrams. It's just kind of so here's the fourth point. This view of mechanisms, the one I've just said, which some people can't see how I can simultaneously adopt microstructural essentialism and reject the reduction of chemistry to physics, but I do, and I will do that here. So this view of mechanisms, just like my view of substances, has no tendency to support the reduction of chemistry to physics. And basically the reason why that's so is that all these really full explanations that physical laws are involved in, they presuppose lots of organization that has no independent explanation from on the basis of physical principles. So there's no reason. You're not explaining ex nihilo. And so it's all about the details. There's a lovely quote from Lawrence Sklar in a recent paper. I mean, the interest in the reduction in emergence debate isn't whether X is reducible. It's what comes out, the details of why the failures happen where they fail, or why they succeed where they succeed. It's the details of those intertheoretic explanations which are really interesting. And I'm going to have something to say about that, about molecular structure. Okay, so here is a really famous book on, I can't remember, there's two really famous books from the 1950s about structure and mechanism in organic chemistry. One is by Gould and one is by Christopher Ingold. One is called Structure and Mechanism in Organic Chemistry, and the other one is called Mechanism and Structure in Organic Chemistry. So I can't remember which one this is. But anyway, Gould, Edwin Gould, it's a really famous book, and he does this marvelous thing of saying what he means by a mechanism. In the ideal case, we may consider the mechanism of a chemical reaction as a hypothetical motion picture of the participating atoms. Such a picture would presumably begin at some time before the reacting species come together, approach each other, then go on to record the continuous paths of the atoms and their electrons during the reaction, and come to an end after the products have emerged. Okay, so so far so idealistic, but of course, and he goes on to say, well, of course, we don't have access to that. What do we do have access, however, are mechanistic explanations in which there are one or more crucial instants during the course of the reaction. So these are key things happening, and these are the steps that I was talking about earlier on. The making and the breaking of bonds. Basically, there's only a few ways that can happen. You can change what's on the end of those bonds, but you can only make or break bonds. So that's what happens. So that's what we're going to see, a series of steps like that. Sometimes there's a lot of them happening together, the mechanisms we talk about. So of key interest is the slowest or rate determining step. As everybody knows, that there are rate determining steps. At the moment, there are lots of the slowest pace in the distribution, for instance, of teddy bears, imported teddy bears in England, is going from where they arrive in England, being put on the back of trucks because there aren't enough truck drivers. You've got to wait a long time for a truck driver to turn up. So that's the slowest step. So that's the thing really that determines if all the other stuff is happening very quickly, then that's the thing that's going to determine overall how long the whole process takes. So it's just the slowest step you need to look at. And that's the key insight of something called chemical kinetics, which is just a study of how fast chemical reactions happen and how external interventions change that. So Mark Goodwin has got a nice sort of description of this it distinguishes between these two things that Gould names as thick, that's the motion picture, and thin mechanisms. Thin mechanisms are the steps. I think it's important to emphasize that the thick and the thin mechanisms are just perfectly consistent with each other. Looking at one rather than the other isn't a change of view. It's just well, it's just a focus on the things that matter, and the things that matter because, you know, we can get empirical access to those to help us reason about what the mechanism is as a whole. So philosophers might be skeptical about the idea that chemical reaction mechanisms can all be broken down into a few elementary kinds of steps. But, you know, as far as I know, I can see that it's true, and the idea's got a history. So in the 19th century, when there was a lot of back and forth, people knew that they had to have a theory of structure, and a theory of structure is a theory about how there can be atoms can be arranged in different ways. And they knew that there had to be such a theory of structure, because they could see that there were chemical substances, different chemical substances, that had consisted of the same elements in the same proportions. And because they were different, separable, chemically distinguishable substances, they had to be the same atoms arranged in different ways. And explaining that is a theory of structure. That eventually emerged in the 1860s. But all this time, and that gave you an idea of a bond or valence, which is the root of everything. When I talk about a classical structure, I mean a bunch of atoms connected by classical chemical bonds. And when I say classical, I don't mean anything to do with classical mechanics. I mean something to do with the theory that Auguste Kekule and other people and other chemists came up with in the 1860s, and they learned to reason about how there could be different atoms could be arranged in different ways within compounds connected to each other in different ways. So in the 19th century, there were, you know, where does the source of the valence come from? Is it two different kinds of atoms, so positive and negative atoms? Is it electricity that's at the heart of it? That was the dualistic theory. And there were different something called the type theory, which I won't go into. It's basically a substitutional theory, and each of them had their problems. Type theory is basically really unclear. I still sometimes wonder. I'm not sure I can get my head around it. It's nothing quite like anything else. It kind of died off when the Kekule theory emerged. But dualism could explain chemical, why atoms might be joined together by electric forces, but they couldn't explain why, for instance, you could have two atoms that were the same connected together. So chemists know of lots of examples of that. Hydrogen bonds to hydrogen in hydrogen gas to give us diatomic molecules. So if there's an electric change, how could electricity be? They're both the same. You know, how they couldn't, they're not opposites. So you could understand how sodium and chlorine would come together in that, because they could be, you know, one would be positive and one would be negative. But hydrogen, chlorine to chlorine, that's a mystery. In a pair of lovely papers in 1913 and 1916, Gilbert, is it Newton? Anyway, G.N. Lewis, those chemists all know him, gave a kind of a synthesis of this, where he just took the notion of an electron and said, well, if we understand that there could be two kinds of substance, polar and non-polar substances. This is from the 1913 paper. Then the sharing of electrons in some way could give you a continuity of different kinds of substance. So on the one hand, if the electrons are shared very asymmetrically, then you would have electrostatic forces between between atoms with positive and negative atoms. That would what would be happening in things like salt. Then if the electrons are shared equally, you'd have this thing called the covalent bond. And the idea that ionic and covalent bonding is on a continuum is just a lovely unifying idea that's in Lewis's two papers from 1913 and 1916. And everybody's very, people are very often very rude about this, especially, oh well, along comes quantum mechanics in 1925 and sweeps this all away. But really, I mean, compared to the madness of quantum mechanics, this is really good stuff, and these explanations have lived on, although it's hard to make sense of exactly how valence is supposed to work. But that's still a bit of a mystery in quantum mechanics, I've got to say. And the other thing is how Lewis's theory moved directly on to provide an account of reaction mechanisms in organic chemistry from the 1920s onwards, developed by people like Christopher Ringgold, in which they drew directly on Lewis's covalent bond, as we'll see, because they said, well, what are bonds, chemical bonds made of? Those sticks. Well, when they disappear, when you've got a bond breaking, you've suddenly got two electrons to account for. So you've got to have them going somewhere, and that's what a reaction mechanism is. So in a really kind of nice, elegant way, they commensurated the physical makeup of the bonds. And this idea came from Lewis. There was no sort of theory telling you, there's no underlying physical theory telling you what was going on. Lewis has had a go at explaining chemical combination in these terms. And you can see this conception at work very nicely in this. It's not done quite right here, but it's all there in these mechanism diagrams. Let's go into detail. We've got an even worse diagram in a moment. I just want to focus on some key things. Firstly, you've got these. You can see those little arrows. So there's two mechanisms here. There's Sn1 mechanism and the Sn2 mechanism. So there are two kinds of mechanism. I said mechanisms can coexist. Well, these two mechanisms can be happening right alongside each other to different molecules in the same sample of alkyl halide. And it depends on conditions. You can favor one or the other, and also through the structure of the thing. So there's the idea. Mechanisms are different pathways that can, as it were, coexist at the population level. So if you look at the Sn1 mechanism, that just means it's Sn1 means it's a unimolecular rate determining step, and it's nucleophilic substitution. So that's the Sn, and 1 means it's a unimolecular. So what that means is that the slow step in the Sn1 is it only involves one molecule, and so its rate will only depend on the concentration of one molecule. Anyway, but you can see on the left hand side of the Sn1 mechanism, you've got a little arrow, and what that arrow means is just the L atom is going to receive the two electrons that make up the bond that connect it to the carbon atom there. So you've got a carbon atom in the middle connected to 4 other atoms, and the L atom is going to receive both of those electrons. Now, one of those was its electron, because that bond was an shared electron bond. But it's now got an extra one because both of those electrons have gone to the L atom. So the L atom is now going to leave because it's got no bond to the rest of the molecule, or the rest of the species, and it just heads off. But it's got an extra charge, so it's L minus. You can't. That unfortunately is not. It said plus L there, and then you have an attack by something. You get this structure. And basically you get a mixture of two. You can see on the right hand side of that mechanism, you get a mixture of two products. then there's the Sn2, which just means it's a bimolecular or two molecule mechanism, which requires that two molecules have actually got to come together. So it's bimolecular. And so the chance of that happening is depending on how many of both types of molecule there are. So its kinetics is going to be what's called second order. Anyway, never mind, go into that. So you can, through the mechanisms and the products, through the kinetics, sorry, and the products, you can tell the difference between which of these mechanisms is predominating. So in the second one, you get an inversion, because the atom comes around. It's like an umbrella. You know, when on a really windy day, when your umbrella is pulled out. Well, imagine that process. That's what's happening on the Sn2 mechanism. You've got an atom here, and then this structure goes boom, and I can't do it with my hand, but you know, your umbrella is broken out, and then you have this thing in the middle with the square bracket. That's a kind of a intermediate state, high energy. It's not going to live for long, and then it loses the leaving group. That's the chlorine atom, which then leaves, and you have an inversion of structure because the chlorine atom, the new bromine atom comes in on the opposite side of the chlorine atom, and so you have what's called an inversion of structure, which have been known about since 1895. That's called the Walden inversion, and this mechanism explained why you would have that inversion of configuration. Here's another really complicated reaction. This is the Gould-Jacobs reaction. That's Gould as in Edward Gould we were quoting a moment ago. But I don't need to do anything, but here's the reaction, and then the thing on the right with lots and lots of steps is the mechanism. All I want you to focus on is the way that the little arrows, here the arrows are very elegantly done. You used to get marked down when you're an chemistry undergraduate for putting the arrows in the wrong place. You have to draw them right. So those little arrows, they are the transfer of electrons from bonds, where you go in the middle of the bonds onto an atom to give you something that's charged. And when the bond disappears, then the atom that was bonded to the rest of the molecule in that place just has to float off. It's something else now. It's one of the other products. So you can see that happening. And once again, you just have this, you know, Lewis gives you this way of commensurating these mysterious bonds and seeing chemical reaction mechanisms as processes which involve the conversion of bonds into charges and back again as part of the overall chemical process. I think it's marvelous. I bore anyone with for hours on these topics. So here's the concrete proposal. Mechanisms of pathways. The chemical reaction is a process defined by its reagents and products. Reagents and products are themselves characterized by their structures. That's the microstructural essentialism. A reaction mechanism must therefore be a pathway between reagents and products. Each such pathway is characterized by the intermediate structures formed en route. Molecules in the same population may follow different pathways between reagents and products. We just said that. So you'll get a mixture of products, and evidence for which pathways actually occur include how the products, and secondly, how the rate of reaction, that's the kinetics, change under intervention. So when you heat things up or cool things down, add more of this or that reagent, change the solvent, these are all things that change things. And there's a lovely way of conceiving as mechanisms as possible pathways. It enables you to explain how you get this lovely kind of eliminative inference, very elegant kind of eliminative inference on, I think, well, I'm just having a look at the time. I've probably used up far too much time because I've got a whole lot of quantum mechanics to go through. But so basically Roald Hoffman in his book, The Same and Not the Same, I've got this lovely example which I urge you to look up. So the reaction on the left there, I've just scanned in the diagrams. I think my camera is playing up. I don't know if you can see that. And the camera on the and the reaction on the right, that's a reaction, and then 1, 2, and 3 on the right are three possible proposals about how the reaction might occur. Number 1 is a concerted reaction where the two. So basically, what happens is you have ethane on the left turns into ethene, or ethylene as it used to be called, plus hydrogen. So you've just got 2 hydrogen atoms leave as a hydrogen molecule, that leaves a free valence on each carbon atom, so they bond to each other, giving you this double bonded molecule of ethene. So number one is the concerted reaction, where the two hydrogens leave from two different carbons. Number two is it's a two-step reaction where the two hydrogen atoms leave from the same carbon atom. And the third is a chain reaction. You've all heard about chain reactions, where the light comes in. That's the H nu. That's the right-hand side of Planck's formula. The H nu comes in, and it's a burst of energy which breaks a bond, basically, leaving you with these dots. And those dots, amazingly enough, they signal free radicals, but they are unpaired electrons. That's a little electron sat right there. And that because sometimes you have to have electrons singly, they're not as part of pairs, they're not buried into atoms, and we've got them there to tell us we've got a free radical, which is an unpaired electron. And then the chain reaction, you pass on the free radical, you collide with another molecule, creating some more free radicals, and so on. And the really nice thing about Hofmann's, I think, if you love chemistry, it's a fantastic example. It's only about 4 pages long, of something which is of so much interest in philosophy of science at the moment, the idea of eliminative inference. And Hofmann just tells you how, within the context of structure theory, there's only 3 ways that this reaction could happen. Try and think of some more. Maybe there are some others. But anyway, you can use isotopic labeling to knock out 2 of these reactions. That's number 1 and number 3. And he says that just leaves you with number 2. Because if just by isotopically labeling the ethane with deuterium in different ways, you can go through a series of experiments that knock out 2 of the possibilities to say these are inconsistent with the products we're getting. So that's a lovely piece of, but it's all founded on. I don't think that this is the kind when, for instance, Carl Stanford, who's worried about these kinds of about eliminative inference, these aren't the inferences he's worried about, because these are the bread and butter of science. They are these kinds of, we've got all the possibilities here. That's always the problem with the eliminative inference, and it's structure theory that tells you the different, well, there's only so many ways that atoms can be bonded together given the rules of valence that were worked out in the 1860s. Okay. I now move on. I said I'd move on to the mechanism of reduction and emergence. How much time do I have left?
You still have around 20 minutes.
Sorry?
About 20 minutes. 20? Yes.
Oh, brilliant. Okay, that's good. Okay, I shall still have to speed up a bit. Thank you. I'm trying to increase the volume. Okay, so then, and this is one of those things, I speak to people, when you have those conferences, conference lunchtime, I've been sat with someone and, I said, I'm a microstructural essentialist, but I don't believe in the reducibility. Can you still hear me?
Yeah.
Yes,
my camera's gone off. I've got a dodgy camera on this. I think what I might do is log back in on my other device. This laptop has always had a I'm so sorry, folks.
Yes, but we can see the slides, and we can
I'll tell you what, for the questions, I'll just carry on as I am, because you don't really need to see me.
Yeah.
Okay, so sometimes when you're sitting around, people say, well, if microstructural essentialism is true, then reductionism has got to be true, because blah blah, and then because what else is something but it's microstructure, it's structure at the molecular scale, which is just atoms and electrons, isn't it? So that's reducibility, So here is why I don't think those inferences follow, and I think they can be resisted. I've got that as far as I can do. So there's 3. I've talked about pathways. Well, here are 3 pathways from mechanism to reduction, and I think they're all blocked I don't know, maybe there are others, maybe I haven't got all possibilities. I think there are insuperable injections to each of them. Basically, there are different ones, slightly different ones in each case, but basically the case is that these explanations, I don't deny that underlying physical laws play a really important part in building up our understanding of why things go the way they go, or why substances have the structures they do. But those structures, those explanations always make special substantive assumptions about organization, which come from the special science. Now, of course, all of that is compatible with a weak ontological reduction, where we don't really expect explanations, intertheoretic explanations, to look reductionistic. But mere compatibility is not the same thing as being able to infer reducibility from mechanistic explanation. So here are the three candidates I could think of. One is theoretical identities. The second one is the reducibility of molecular structure. We've said how our understanding of mechanisms in chemistry is really just an application of our understanding of a case-by-case, a substance-by-substance understanding of how things are, the structure of things at the molecular scale. So if molecular structure is reducible, then mechanisms are reducible. We're just going from one structure to another. And the final one is like the retreat point. I'll say a little bit about the completeness of physics, but I think I've only really got some grandstanding to do about that here today. But here we go. So the first one is theoretical identity. So there was a mind-brain identity theory. It seemed to me that the theory itself, one might well say, oh, well, is pain really equal to C fibers firing? Sorry if that is a terribly outdated example, but it's up there along, this is part of the history of the philosophy of science. Pain equals C fibers firing. I don't know if people, I've got no idea whether C fibers are still a thing, but water is H2O. I will defend that, against classificatory pluralists who say, oh, water's not H2O. I always ask, well, what else is it? And would you, who would you trust to determine what should be in your water, and so on. But anyway, that's only looking from the point of view of chemistry when I say that. So my point is that one could accept both of these identities and none of the things that follow about, for instance, the only things happen at the lower level. That they don't give you that. I mean, the reason why I'm going to say that in water is H2O, the only sense in which that's true is in which water on the left-hand side of that identity is a substance, and water equals H2O. There can only be an identity there if we take on the right H2O not to be an H2O molecule, but a substance whose empirical formula is H2O, and that's a different proposition entirely. So water, I will accept that, and that the only substance we have whose empirical formula is H2O is in fact water. So that's fine. That identity goes through. And how do we make water? Well, we bring H2O molecules together. Now, identity theorists assume that establishing a relationship like this, and this is in Smart's version, you look at that, it seems to me the non sequiturs just abound in those articles. He briskly dismisses, emergentism on the basis of these identities. But, it seems obvious to him, everything that water does is going to be work done by H2O molecules. And that's true in a real sense, but we've got water is a complex congeries of different species. I'll talk about it in a minute. So Putnam once claimed famously in 1975 that the extension of water is the set of all holes consisting of H2O molecules. And this is where classical mereology is just the all holes, that's an application of, but it's just not true, because water the pure substance contains other things. And I'm not talking about impurities, I'm talking about all sorts of things. So there's a process of self-ionization where H2O molecules come together, one of them loses a proton to the other one, so one of them protonated. It's about 1 in every 10 million or so. And that gives you enough polarization. Water molecules are polarized as well. So there's a significant amount of hydrogen bonding which affects their interactions with each other. They interact very much more strongly. So there's all sorts of anomalous things about water, and physical chemists say this, and condensed matter physicists. There's a lovely article, what's so special about it? And there is something quite special, which means it's like the worst example for microstructural essentialists, because there's something really complex going on in how the molecular interactions produce the macroscopic substance. So one example of this is the Grotus mechanism, so one of the anomalous things, water's got an anomalously high boiling point, it's got an anomalously high latent heat of vaporization, all that. It's also got an anomalously good electrical conductivity for a substance of its type. Disastrous if you're in the bath and you drop your electric radio into the bath. But anyway, and one of the reasons why that is, I mean, this just looks like a holistic explanation to me. One of the reasons why that is that when you pass charge across the water, you don't need to wait for a charged particle to make its way across the water. If you see on the right, the Grotus, what I've called the Grotus mechanism there, which was first hypothesized under a dualistic idea about the structure of water in 1805, which when it was thought to be HO, it's in Dalton's time. The details matter. No, it's not exactly clear still how it happens, but you don't need to pass, no charged particle needs to go from one side of the water to the other for the charge to cross the water. Instead, you get a concerted process where, imagine if we were all, when people are putting out a fire and they pass buckets of water to each other. Well, it's just like that. So what we're passing is excess charge, except in that case, there's a disanalogy because we're actually passing material buckets of water following down the chain. Well, here we've got chains, and by a concerted process, you can add an excess charge. You can see how in those two diagrams there that would happen. So the charge goes from one to the other very quickly, tens of times faster and more efficiently, without having to fight your way through the crowd. You can just, as it were, email it there. So there's a lot of organization that's presupposed at the substance level, at the macroscopic substance level, and that's what the causal powers of water depends on. Now, of course, I don't think this argument wins I don't think this argument is automatically decided in favor of the strong emergentist, but I just think it's just not at all clear, because the way that these explanations happen presupposes significant explanation at the, I've not used that word yet, higher level, at the level of the substance. It's not clear at all. Let's see how that explanation goes. Which parts of it are reductionistic? There's a debate there to be had, but the point is that it's not won by the reductionist, because the mechanisms as we understand them working in water presuppose significant organization. And the key thing, interactions between H2O molecules during which some of the H2O molecules go out of existence in the process. So it's a genuinely holistic explanation. So the next, sorry, I'm just going to go back a bit. They're going back, theoretical identities. The next one is the reducibility of molecular structure. I'm now going to give you a 5-minute explanation of why I don't think molecular structure is reducible, and therefore why that is blocked. In fact, I think in a really interesting, super interesting way, and I'm in a minority of about 2 or 3 here, I think we should call it emergence. Never mind, we don't need to think about strong emergence for the minute. So let's go. Sorry, I've got to go back one. So structures can't be derived from quantum mechanics. When people make the original reductionist claim, that's the claim. This is not just a computational difficulty, though that is a problem too, typically. It's a problem in principle. It's a problem like it's a many-to-one explanation, because the thing that we would derive, supposedly derive thing, if you look in theoretical chemistry textbooks, they say, oh, we're deriving thing, we're solving the Schrodinger equation. Well, in a way we are, but we shouldn't think of that solving. We're identifying things which approximately approximate to solutions to the Schrodinger equation, but we shouldn't think of that as anything like a derivation. It's a construction of things which satisfy certain constraints. So the candidate exponans, the molecular Schrodinger equation, doesn't distinguish between isomers. Isomers are, as I've already explained, these are molecular species with quite different structures and symmetry properties. So ethanol, for instance, and dimethyl ether, you can see them in the thing. They're just different substances. Atoms arranged in different ways. We can separate them. They have different boiling points. One is the active ingredient of whiskey. The other one is, well, it's not. The other thing it crucially fails to do, I'll get onto that in a minute, the Schrodinger equation applies blindly to distinguish to systems with so-called classical molecular structure and systems that lack it, like metals. So overall, quantum mechanical explanations of molecular structure look nothing like the derivations associated with the reductionist accounts of the special science. And on the ontological reduction side, they look nothing like the determination. So I always think, why would you think that determination is going on, that it's the lower level that determines everything, if there's nothing like determination going on in our intertheoretic explanations? There's a kind of why would there be a mismatch? Here's the content. So explanations of molecular structure within density functional theory, which has completely taken over molecular quantum mechanics and in chemistry and condensed matter physics in the last 30 years or so. Explanations of molecular structure within density functional theory depend on what are normally regarded as approximations. It's called the Bourne-Oppenheimer approximation. So my view of this, and this is why I have it, and it's a minority view, I argue that those approximations should be taken seriously and that they represent substantive additional assumptions about the well-defined physical conditions within which classical structure arises. So there's 3 of them, and this draws on joint work with Robert Schoonmaker, who was part of the Durham Emergence project, which ran from 2013 to 16. And the 3 conditions are the adiabatic separability of nuclear and electronic motions. I'll explain all these. The localization of the nuclei, and restriction to a single classical structure. There, what I mean is no tunneling. So we'll basically the rules of the game here are to say that structure is emergent. You've got to say that a structure is, as it were, dependent on something more fundamental. So emergence is very often characterized as dependent novelty. So we've got to identify a kind of dependence and a kind of novelty. Well, dependence is easy because if you take away electrons and nuclei, there's nothing left of a molecular structure. So there's a kind of straightforward weak existential dependence there. I now identify 3 kinds of novelty associated with these three physical conditions. One is adiabatic separability. So anyone who's done kind of a course in Quantum Mechanics 101, when you do the 1 electron system in an electron confined in a 1 electron box, if you keep the 1 electron box, you can have the walls moving, as long as they're moving slowly enough that the electron's wave function can adjust smoothly and continuously to the change in the position of the walls. If it doesn't, you've suddenly got a quantum situation. The electron says, "Oh, my ears and whiskers, what do I do now? We'll have to recompute." But if you do move it slowly, that the wave function with the same form just adjusts to the different parameters. Now, the same thing is assumed, it's called adiabatic separability, is assumed to apply to electrons and nuclei. Now, this is sometimes justified on the basis, in chemistry textbook, it's a very weak justification, the fact that nuclei are much heavier than electrons. But that's always the case, right? I mean, that happens in metals where adiabatic separability is not assumed. So that's something's different that's going on here. It's the difference in weight, which is the mass, it's a standing condition, so it can't be anyway. It's actually a function. I think it's a substantive dynamical assumption. It gives you a kind of effective field theory. You get a separability of the electrons, the electronic and the nuclear parts of the total wave function. Basically, the nuclei can react to kind of an undifferentiated carpet of electron density, which can be regarded as, effectively static because the electrons are moving so fast. And then the electrons can see basically instantaneously static nuclei, and that's what's going on. It's a bit like, so I've seen an elegant organization, but when you see parents walking through a park and they've got dogs and they've got children running about, and the children and the dogs are constantly adjusting to this. So the parents are walking more slowly and the dogs and the children are moving much faster, and the dogs and the children are constantly checking back where are the parents. So they know where the parents are, and they constantly adjust, as it were, the center of their much faster motion to the parents' stately progress along the path through the park. So that's kind of what's going on here, with the electrons are constantly adjusting, just instantaneously are able to adjust. And what it means is that the two things move in lockstep, and the function of the quantum system as a whole is a function just of the nuclear configuration. That's a special condition, and it means you can do these things of drawing these potential energy surfaces, which you've probably seen, which are kind of maps of the total energy of the system as a function of nuclear configuration. If you don't have that, you can't draw those surfaces in that way. Simple. They come along with that assumption. And these things don't hold, these assumptions don't hold in metals and superconductors, which, physicists scratch their head when we say this, but we're just trying to identify some systems where these assumptions aren't made. And therefore that assumption plays no part in the kind of structure, and we don't expect them to have that kind of structure. Another kind of thing, I think this is even more interesting, is nuclear localization. So sometimes nuclei we don't just instantaneously put nuclei at rest. We can separate them from each other, and we can localize them by their interactions with the electron density. And what that means is that the nuclear statistics, either whether, for instance, the nuclei are either bosons or fermions, doesn't make a difference to the way that the overall wave function. The wave function will evolve in the same way, regardless of whether they're bosons, fermions, or whether they're assumed to have classical statistics. So, and these things can be localized for a long time. So you can have two nuclei in the same molecule, two, for instance, carbon-12 nuclei, which are bosons, and if you take seriously the idea of particle permutation symmetries as representing a real physical process, then these bosons don't ever swap. They're kept apart for longer than the lifetime of the universe. So effectively, contra Weil, Hermann Weil, nuclei can be given alibis. Remember, there's that famous thing, nuclei, you can't give them alibis because you can't say where they aren't. Well, if you've got one trapped by its interaction with something else, then you can, because we can stick a label on it. It doesn't come with an identity, but we've got a localized quantum of boson density that we can say. And that's a really interesting thing. So I think nuclear localization is not deduced from exact quantum mechanics. It's not, in no sense is it. It's merely shown to be dynamically consistent with it in the sense that it doesn't make any difference to the way that the wave function evolves. So you posit it just like like you do in an effective field theory, and show that it doesn't make any difference to the way that the system evolves. You're not deriving it from anything more fundamental. You know what you've got to get to, and then you say, well, this doesn't actually violate the underlying laws. And there's a really interesting example of failure of this. If you protonate methane, so remember, methane is CH4, but if you add a proton to it, that's CH5 plus. And the two of the protons, because obviously methane contains other protons, two of the protons are so closely lying that they're not separated, and you have to take their exchange process into account in describing the way the molecule behaves, and this is detectable in its dynamical behavior. So classical molecular structures are a special case, and they arise in special conditions, and we shouldn't think of. What's really interesting is that this corresponds to a kind of emergence that Paul Humphreys talks about, transformational emergence, which is where the interactions between a group of things change their kind of nature and the way that the fundamental way they behave, so that things we expect of the bosons, which is bosonic behavior, which is exchangeability with other bosons, and that is suspended. It no longer makes a difference to the dynamics of the molecule.
Robin,
okay,
sorry.
And then, sorry?
5 minutes. 5 minutes.
5 minutes, great.
Sorry for interrupting.
Okay, I've just got to, and then the last one is the ban on tunneling. So I won't say very much more about this, but as part of this is one of the things I'm proudest about. Of the Durham Emergence project, the physicists did some new calculations and new analysis of cyclobutadiene, which is a molecule that we thought would be interesting because it challenges the classical notion of structure, and challenges the classical notion of structure because I don't know if you can see it there. Basically, it's there's the carbon atoms tunnel between two positions. So it's between two rectangular positions, and the electron density moves as well. So you can see the two structures there. You imagine they're just two rectangles round the other way. Now, from the point of the quantum mechanical point of view, well, we might think, well, the one at the higher, backtrack a bit, you can detect both of these structures at different scales in the X-ray and the IR response. So if you do an X-ray response, you'll catch the rectangular system. That's in the infrared response, averages out between these two things to give you a square. From a quantum mechanical point of view, each of the wave functions can be used as a basis for constructing the other. So we might say, well, neither of them is more fundamental. But the thing is that tunneling is a normal quantum mechanical behavior. We've already had a discussion of this more P.W. Anderson, Philip Anderson's more is different paper. Well, there he's got this really famous discussion of ammonia. Now, ammonia is another case, I think, because there, I argued with some of the kind of more reductionist minded of the condensed matter physicists on the project, because the thing that always strikes me about Anderson's discussion of ammonia and the whole discussion of ammonia is, where does the ammonia double well come from? So there's no kind of deep derivation of it. We know what we've got. Why is there a barrier to the oscillation between the two Sputnik structures of ammonia? Well, because the carbon atom's got to move through the plane of the three hydrogens, and when it's doing that, you're going to have a strange structure, so it's higher energy. So that's why that fundamentally is why there is. We can explain it with some organization there. There's nothing fundamental going on. We just give ourselves the two different quantum states that it's tunneling between, and say that actually the pure quantum state, the eigenstate of the overall Hamiltonian, is just the one which is a superposition of these. Anyway, that's going into a separate discussion. I'm going to come back to that. Okay, so that's why I say chemistry is the molecular structure is emergent. Classical molecular structure is emergent because there's the suspension of certain straightforwardly quantum behaviors like tunneling, like quantum statistics, the expression of quantum statistics in the dynamics of a quantum system, and in the adiabatic separability of the nuclear and the electronic motions. Okay. Now I've said right at the beginning, I think I've got on my last slide, we've got three theoretical identities: the reducibility of molecular structure and the completeness of physics. Now I'm just going to do some grandstanding here, and I apologize for it because there just isn't time to say more about all of this. But many people on the reductionist side of the debate, they hear everything I've said and say, yeah, but another theory is going to come along, in principle, and that's the kind of thing that scientists say. And Weinberg says this in his that 2001 book. There's a chapter on there where he talks about reducibility in principle. He's talking about how he doesn't really disagree with people like Mary Midgley, who was a tremendously anti-scientistic and anti-reductionistic philosopher who was based in Newcastle, recently died. And he was saying, oh, you're not you, because we don't really disagree, because we all agree on reducibility in principle. I very much doubt that's true in Mary Midgley's case. And Weinberg never gives an argument for reducibility in principle. And it's not hard to see why, because what he means is, well, there's very little we can actually explain in a kind of rigorous sort of way, but somehow a future theory that we don't currently have will come along and give us equations that, even if it did come along, we couldn't solve them. And in principle, those explanations, even though that theory, we can't use it to explain anything, in principle, it does explain everything. So that's the kind of the physicist formulation of it. In metaphysics and philosophy of mind, there's a different formulation, and I've never really I've seen one good proposal on what it is, for what the completeness of physics, and that's what to advertise the Routledge Handbook of Emergence, which Brian McLaughlin very kindly wrote an article for on British emergentism. But there he talks about a kind of, in the same way as there's a distinction in mathematical logic between syntactic entailment or derivability, the proof theoretic idea of entailment, and a semantic idea of entailment, where the models in which of one are also models of the other. So what's true in what models, if a sentence is true of one, it's true of the other. So his idea was that there'll be a kind of the notion of determination that that reductionists want. And it's an ontological one, somehow the worlds at which this is true, that's true too. So where you fix things, I mean, it's all very well, but the question is, for me, where is the evidence? Where do we get to this from the way that physics over time, over the centuries, has interacted with other sciences and even conducted its own explanations? So I think it's that kind of determination is a bad model, because it doesn't mirror anything that happens in science, or only very rarely. So the two philosophers, as I say, it's a crucial assumption in, for instance, exclusion arguments, which is one way to get reducibility. So Jae-Won Kim style, and I've seen in the context of mechanisms, philosophers of science like Alex Rosenberg explicitly running exclusion type arguments. Well, of course, once you've got a mechanistic explanation, it means you can just go to the lower level and that causally excludes everything else. So all your functional identifications, where you can just throw away the, from an ontological point of view, you can throw away the higher level functional theory. So I just don't think that's a non-starter, because to make a causal exclusion argument work, you've got to have the causal completeness of the lower level, and that's a kind of high level metaphysical premise that we just don't have evidence for, and I would be very, very pessimistic about having evidence for. The cautionary tale here is in the history of determinism. So sometime during the 18th century, and there's a lot of blaming of the French going on in Britain at the moment, so I'm not going to blame the French. But sometime the Newtonian mechanics hit the French Enlightenment and French mathematics in the mid-18th century. If we go back to the early Newtonians, the idea that Newtonian mechanics is part of this massive worldview, mechanistic worldview with things crunching, it was just absent. I examined a thesis a couple of years ago looking at all the people around Isaac Newton, the people around the people he was talking to in Cambridge and the philosophers, and their project was to show how the operation of Newtonian mechanics is consistent with a literal interpretation of Genesis and the Old Testament. That's the program. It's not, we're not setting it in the sense of, oh right now. So then what happens is that Edmund Halley makes this marvelous prediction about the return of Halley's comet 40 years hence. Laplace, Pierre-Simon Laplace in 1805 gives, I think, what's got about one of the worst arguments in the history of philosophy. And clearly, any historian of philosophy will say that means he thinks he's asserting something that he thinks is already established, that there's no need to give a good argument for it. And basically the argument is, oh, well, Edmund Halley managed to predict the return of his comet. Therefore, reality as a whole is deterministic. Therefore, that honestly is the argument. So it's over about two pages. Therefore, and this being the philosophical essay on probability, that means all probabilities must be epistemic probabilities, which I get the Laplacian notion. Anyway, so it's a premise in the argument. He wants to get where he's going, but it's a terrible argument. But somehow, by 1805, he thought it was a safe assumption. So I think it would be really interesting to find out exactly why and who started making this assumption that philosophical determinism is forced on us by the success of Newtonian mechanics, because it's absent in among the early Newtonians, and it's only when where we hit the French Enlightenment. I think there's very good reasons why it would have been absent earlier on. I think it's an unreasonable assumption. Anyway, so history of determinism, history of causal completeness of physics. I'm very pessimistic about these large-scale assumptions doing a lot of work in telling us how we should understand the relationship between, for instance, biology and physics, chemistry and physics, and so on. So thank you very much.